Hypervelocity star clusters are a subject of intense study because they challenge our understanding of gravitational dynamics in galaxies. These clusters, which can be observed traveling at speeds that allow them to escape the gravitational pull of their host galaxies, provide valuable clues about extreme astrophysical processes. One scientifically rigorous explanation involves gravitational interactions near supermassive black holes. When a binary star system or a star cluster passes close to a supermassive black hole, tidal forces can impart tremendous kinetic energy to one or more stars. This process, sometimes compared to a gravitational slingshot, can accelerate stars to velocities of several hundred kilometers per second. Could such interactions be the primary mechanism behind hypervelocity clusters? Theoretical models and computer simulations support this idea, yet observational evidence is still being gathered to confirm the details. Another plausible scenario involves the dynamics of galaxy mergers. When galaxies collide, the resulting gravitational chaos can redistribute energy in unexpected ways. In such events, stars and clusters in the outer regions of merging galaxies may receive a boost in velocity, effectively ejecting them into intergalactic space. Observations of hypervelocity stars in our own galaxy have lent some support to this model, although determining whether these stars originated from mergers or central black hole interactions remains a matter of ongoing debate. How do we decide which mechanism is more likely? Critical evaluations require high-precision measurements of star velocities, trajectories, and their chemical compositions, as these can provide clues about their origins. An additional layer of complexity comes from the influence of dark matter. Since dark matter governs the overall gravitational potential of galaxies, its distribution affects how energy is transferred during dynamic interactions. For instance, if a galaxy has a particularly concentrated dark matter halo, the gravitational forces might be stronger, thereby affecting the conditions under which stars can be ejected. Observational campaigns using large telescopes and space-based instruments aim to map dark matter distributions indirectly by studying the motions of stars and clusters, including those moving at hypervelocity. Could variations in dark matter density explain differences in ejection speeds observed among hypervelocity clusters? This remains a critical question that drives further investigation. It is important to note that while both scenarios, interactions with supermassive black holes and galaxy mergers, are supported by theoretical models, each comes with its own set of challenges and uncertainties. For instance, accurately simulating the environment near a supermassive black hole requires incorporating complex physics such as general relativity and hydrodynamics, while galaxy mergers involve chaotic, multi-scale interactions that are difficult to predict with precision. Researchers continue to refine these models using state-of-the-art computational techniques and to seek observational evidence from surveys and targeted observations. Hypervelocity star clusters provide a rigorous testing ground for our understanding of galactic dynamics, gravitational interactions, and dark matter. Through detailed simulations and careful observations, scientists are critically evaluating the mechanisms behind their ejection from galaxies. Can the precise measurement of their velocities and chemical signatures eventually distinguish between the supermassive black hole and galaxy merger scenarios? Ongoing research incorporating both theoretical and observational approaches is essential to answer this question and to deepen our understanding of these fascinating cosmic phenomena. Hypervelocity star clusters refer to groups of stars observed to travel at speeds high enough to overcome the gravitational binding of their host galaxies. Rigorous observations and spectroscopic measurements have confirmed that these stars exhibit velocities significantly above typical galactic escape velocities. Critical evaluation of these measurements emphasizes the importance of high decibel data and statistical analyses to rule out observational errors. While the phenomenon challenges traditional models of stellar dynamics, the evidence remains subject to continued scrutiny and refinement. For example, precise Doppler shift measurements in the light spectra of these stars indicate they are moving at extraordinary speeds, inconsistent with standard rotational dynamics. It's like discovering a set of runners breaking away from a marathon pack at speeds far exceeding the rest, a finding that must be verified with reliable timing systems. The leading hypothesis for the ejection of hypervelocity stars involves gravitational interactions, particularly slingshot effects during close encounters with massive objects. Rigorous theoretical models and numerical simulations suggest that interactions with central massive bodies or binary black hole systems can impart significant kinetic energy to stars. Critical assessments of these models emphasize uncertainties in initial conditions and the precise dynamics of such interactions. Despite these challenges, the gravitational slingshot remains a scientifically plausible mechanism for the observed ejection velocities. For example, simulations indicate that when a star passes near a massive compact object, gravitational forces can accelerate it to speeds that allow it to escape the galaxy's potential well. It's like using a well-timed slingshot to launch a stone at high speed. The precise alignment and force determine the stone's trajectory and velocity. Tidal forces during galactic interactions and mergers can disrupt stellar orbits, potentially ejecting star clusters from their parent galaxies. Detailed dynamical models indicate that the chaotic gravitational fields during such events can create conditions for stars to gain extra velocity. Critical evaluation of these models highlights that while tidal stripping is well supported, the exact fraction of stars achieving hypervelocity remains uncertain. This mechanism is considered alongside other processes to explain the overall phenomenon, emphasizing the need for integrated observational and computational studies. For example, observations of interacting galaxies have revealed streams of stars with unusually high velocities, supporting the idea that tidal forces during mergers can eject stars. It's like water being forcefully pushed out of a broken dam. The turbulent conditions suddenly propel water into a new, unexpected direction. Accurate measurement of hypervelocity stars relies on high dissolution spectroscopy and precise astrometry to determine stellar velocities. Rigorous analyses must account for potential biases, instrumental limitations, and the influence of local gravitational perturbations. Critical evaluations underscore that while many hypervelocity candidates have been identified, confirming their status requires repeated observations and cross-section with independent methods. This ongoing process of verification ensures that claims of hypervelocity remain robust and scientifically defensible. For example, astronomers compare velocity measurements from different telescopes and techniques to confirm that a star's speed exceeds the escape velocity predicted by galactic models. It's like verifying the reading of a speedometer using multiple calibrated devices to ensure that the reported speed is accurate and free from error. Computational models play a crucial role in simulating the dynamics of star ejection mechanisms and predicting hypervelocity trajectories. These models integrate complex gravitational physics, hydrodynamics, and stellar evolution to recreate realistic scenarios. Critical evaluation of simulations reveals challenges in modeling initial conditions, resolution limits, and the influence of chaotic dynamics. Continuous improvements in computational power and algorithms are necessary to refine these models and align them more closely with observational data. For example, simulations of star clusters interacting with a massive central object yield a range of possible velocities, with some stars reaching speeds sufficient to escape the galaxy. Discrepancies among models highlight the need for further refinement. It's like using a computer game simulation to predict a sports match outcome. While the model provides valuable insights, its accuracy depends on the quality of the input data and underlying assumptions. Alternative theories propose that mechanisms such as interactions with dark matter substructures or energetic outflows from active galactic nuclei might contribute to hypervelocity phenomena. These ideas remain speculative and require further rigorous testing and corroboration. Critical evaluation of alternative models points out that while they may explain some observed cases, they are not yet widely supported by empirical evidence. The scientific community continues to debate these alternatives, underscoring the complexity of galactic dynamics and the need for more comprehensive data. For example, some models suggest that a passing dark matter clump could gravitationally disturb a star cluster, providing an alternative pathway to ejection, though conclusive evidence is still lacking. It's like considering different routes for a long journey. While one path seems plausible, without clear signposts, it remains one possibility among many that must be explored further. The study of hypervelocity star clusters provides insights into the dynamic processes shaping galaxies and their evolution over time. Their ejection influences the distribution of mass and the overall gravitational balance within galaxies. Critical evaluations of these impacts help refine models of galaxy formation and the long-term evolution of stellar populations. Integrating hypervelocity phenomena into broader galactic theories enhances our understanding of how galaxies interact with their environments. For example, tracking the trajectories of hypervelocity stars can reveal information about past galactic collisions or interactions, offering clues to the historical evolution of a galaxy. It's like examining the debris pattern after a storm to understand the dynamics of the weather system that caused it. The runaway stars provide hints about past gravitational events. Understanding hypervelocity star clusters requires an interdisciplinary approach that combines observational astronomy, theoretical physics, and computational modeling. Rigorous data integration from various sources such as spectroscopy, astronomy, and numerical simulations is essential for constructing a comprehensive picture. Critical evaluation across disciplines helps identify inconsistencies and refine existing models. This collaborative approach drives scientific progress by merging insights from different fields to solve complex problems. For example, scientists combine high-dissolution images with detailed computer simulations to predict the likely origins and trajectories of hypervelocity stars, cross-checking findings across methods. It's like putting together a complex jigsaw puzzle using pieces from different boxes. The final image only emerges when all the pieces are carefully examined and correctly integrated. Ongoing research aims to resolve the remaining uncertainties about the origins and dynamics of hypervelocity star clusters with ever greater scientific rigor. Future observations, improved instrumentation, and enhanced simulation techniques will help clarify the mechanisms behind these phenomena. Critical iterative testing of models against observational data is essential to advance our understanding. The continued refinement of theories in light of new evidence embodies the rigorous scientific process at the heart of astrophysical research. For example, future space-based telescopes and advanced computational models are expected to provide higher precision data that could conclusively determine the role of gravitational interactions in accelerating stars. It's like upgrading from a basic map to a high-resolution GPS system. The enhanced detail allows for a more accurate and reliable navigation of the terrain, guiding researchers to the truth.